Okay, hi everybody. In this video, I'm going to go over the solutions to the exam that we had on April 10th, 2023. This exam had 15 questions. It was graded out of 100, so there are 6 extra points possible. In addition to that, the final grades for this exam were increased by 2 because of a because I used the wrong question for number 12. We're going to have a similar problem. This one is slightly harder, so there's a 2 point bonus to make up for some discrepancies in that problem. But generally, the grading on that problem was pretty loose anyway, so it pretty much balanced out when I went back through them. In any case, let's go ahead and take a look at this. So the first question is about Amdahl's law. You have a parallel application where 80% of the code can be parallelized. What is the minimum number of cores required to achieve a 4-time speedup? So there's a few relevant pieces here. Fundamentally, this is Amdahl's law, but there's a few pieces to it. So you might remember speedup and how we want to compute speed up. So for example, if it, considering just the general case where you have a time, let's say you make up a time, you have 100 seconds and you did something in 25 seconds, right? So the speed up would be 4 because 100 divided by 25 is 4. This is a 4-time speed up, so that's what we mean by speed up. So that of course is necessary for this question. It does ask you how to do the speed up. In terms of Amdahl's law, real quick, just as a refresher, I've had questions before the exam about if you need to memorize Amdahl's law, and I think the answer is yes, but you don't really need to memorize it. Amdahl's law is the way that it's something you've probably done before in your life without understanding that it's called Amdahl's law. Amdahl's law is the way that you find out how much faster anything is if you improve part of it. So, for example, if you commute to work every day and part of your commute, maybe you take the highway, and one day you change your route and you take a back road instead, and maybe the back road ends up being faster because there's less traffic. If before it took you 10 minutes to get to work, right? And you were on the highway for 8 minutes, and there's 1 minute here and 1 minute here. Okay, that's fine. And then in our new case, the back road takes us, let's say it leaves us to the same place once we get to here. So the back road takes us, 5 minutes. Okay. Then the way that you would compute this is you've got 2 minutes that didn't change. The time it took you to leave, maybe you have to get on the highway or get out of the main road, get out of your driveway, get out of your parking garage. And the time it takes you to find a parking spot in West Deck, right? So that's 2 minutes that are just not changing. You didn't improve that part of the time. This is the sequential time if we're talking about parallelism. If you're talking about parallel Amdahl's law. But in general, this is the unimproved part. This is the part we didn't change and we couldn't change. And then the parallel part in this case, again, Amdahl's law works whether it's parallel or not. But in this scenario, it's not parallel, but the math is the same. We went from 8 minutes to 5 minutes, right? So we can start to compute the time difference. What is the new time difference, for example, is one question we might ask. Well, the new time difference is going to be 5 minutes. So the total time here is going to be 7 minutes. If you divide 10 by 7, you will get your speed up. Now, you can review the slides. We've gone over a few formulations of Amdahl's law. Some deal directly with speed up, some deal with time. Time and speed up are just really inverted components. So for this problem, if you know Amdahl's law, you can write the formula out. You can plug the numbers in. You can see that because it's a 4 times speed up, I've basically given you the left-hand side of the problem, the left-hand side of the equal sign. I've given you, if you're solving for x, I've given you x. So to do this problem, you do the algebra on the other side to find out the solution. But not everybody memorizes formulas so well. So I'm going to give you the intuition for this problem. The intuition is, let's make up another problem like we just did. If it takes you 100 seconds to do something, okay, and 80% of it is parallel. So we split this into 2 pieces. 80% of 100 seconds is, of course, 80 seconds. This is our parallel region. The sequential region is 20 seconds, right? Our goal is to get a 4 times speed up. What is 4 times faster than 100 seconds? It's 25 seconds. So our goal is 25 seconds, okay? Well, 20 seconds cannot change. So 25 minus 20 equals 5. That means we need to get 5 seconds. We need to find a way to turn 80 seconds into 5 seconds. We need a way, a value, we need to solve for x. We need to say, what is 80 divided by what is 5 seconds? Because 20 plus 5 is 25, which is 4 times faster than 100. So when we do this, I think the answer becomes pretty straightforward, although you can do the algebra to move things over. At the end of the day, it's 16, okay? It's just 16. You multiply, you can multiply this back out and get the original result. So, do you have to do the formula as well? It can help you to be able to write the formulas from memory, but the intuition is the same. If you want to make something 4 times faster, then you take the 2 parts and you solve for the part that's that changes, right? So there's Amdahl's law. So now let's look at the difference between concurrency and parallelism. We accepted a wide range of answers here. There's a formal definition in your slide. But generally, concurrency just has to do with correctness and order. So if you have 2 tasks that are concurrent, it means you can start A, stop A, come over to B, start B, stop B, come back to A, and A will still be correct, okay? And more generally, it can even be you have 2 tasks that are A, 2 of the same task. You can stop one, go to the other one, stop this one, go back to this one, and the solution will still be correct. The result, the outcome will still be correct. So you have even if you have a single core CPU, you can still be concurrent. You can have tasks, take a break, move to another task, take a break, come back to this task, and have it be concurrent. In terms of parallel, or in terms of code, a lot of times that's related to this idea of re-entrance. You can stop what you're doing and you can pick it back up later. Now the biggest difference here with parallelism is that first off, to have parallelism, to do something in parallel, generally it must be concurrent. If you Google this, you'll find some people arguing it doesn't have to be, but usually they're arguing semantics. They're arguing that if you change the way the problem is phrased, then maybe they don't have to be concurrent. In practice, if you're going to make a function run in parallel, it needs to be able to run concurrently also. So that's the first part. The second is this is literally doing two things or more simultaneously. And if you have the property of parallelism, you're kind of assuming this is correct. You're assuming you do these things at the same time and the outcome is the same. Much like concurrency. You can stop what you're doing, pick it back up, and still get the right result. With parallelism, you can do things simultaneously and still get the same result. Like I said, we accepted a number of answers for that. Some answers got partial credit because often when we gave partial credit, it's because it either wasn't specific enough or you only defined concurrency but not parallelism. Or sometimes people wrote too much and they said things that were not true. And so it was difficult to tell what we really think about it. So we graded what was correct and then took off points for what wasn't correct. So the next question for 3, this is straightforward. So what are the nodes in the task, or what are the nodes and the edges in a parallel task graph? We've done a lot of these, so hopefully by now you know that the nodes are the tasks. The edges are the dependencies. Okay? That's it. That's the whole thing. When we talk about parallel task graphs, and again, parallel task graphs are a type of graph. Graphs are used for a lot of different problems. You've noticed lately we're using a graph to show a topology in a distributed memory system. But for a PTG, for a parallel task graph, nodes are tasks, edges are dependencies. Okay. The next question, I'm not going to redraw this entire graph, but there are 2 critical paths. If you drew either or both, we accepted it. The first critical path starts at C, goes through E, H, J, K. That's 7, 9, 11, 17, 20. And then likewise, you can start at 7 again, go to 4, that's 11. 5, that's 16, 17, 20. So C, D, G, I, K, and C, E, H, J, K were both solutions. If you put either, you got credit. Let's see, number 5. We've used PTGs to help us understand how we can parallelize complex problems. What is the worst possible case for a PTG in terms of parallel performance? Well, when we analyze parallel task graphs, we have a metric called width that tells us how parallel our problem can be. So if you wrote width equals 1, you got full credit. That's the describe. At least something, if you describe in more in more detail, then you got more. You still would have gotten credit, right? But this is maybe the shortest description that tells me you know what you're talking about. Secondly, if you drew something that looks like this, and exactly like this for however many nodes, this is a width equals 1 parallel task graph. And so this is obviously the worst case. The worst case for parallelism is we have no parallelism, or we cannot introduce any parallelism. Okay. So what's next? 2 types of data dependencies. We're looking for, now maybe this one should have said 2 out of the 4 types of data dependencies. Maybe that would have been a bigger hint. But we have read after write, write after read, right after write. And these have their names. If I recall correctly, this is output, anti, and flow. Now there are input dependencies, which are read after read. Okay. If you put any, as long as anything on this board right now would have counted as a valid answer. Of course, if you put two of these, that if they match, that's only one answer. But I don't think that ever happened. I think everybody wrote something like this. Now, if you wrote any of these, if you wrote read after read or input, that doesn't count. That was the purpose of discussing read after read, is reading after reading does not generate a dependency. No data changes. This is a relationship, but it doesn't generate a dependency. Okay. And so in the code below, we cannot parallelize the out of for loop due to each iteration having a dependency on sum. So we pointed out in the problem description that sum is a dependency for every iteration. We declare it here, we use it here, we use it here, we use it here. There's no point in this where we can break up our dependency on sum in the current code. So how do you describe the technique to expose more parallelism? There's two phrases that we would have taken. One is scoping, which is how it was described in your slides. If you did assignment, I forget if it was 3 or 4, there's a problem related to this that tells you to look specifically at that slide deck. Likewise, another phrase that you might have used is thread local storage, or TLS as it's sometimes known. This is in the parallel for loop slides. So that's a good description. If it contained these ideas or you describe something that captured these ideas, then that's totally fine. In terms of code, if you had done this the code way, the easiest way to get full credit here is to simply eliminate this line. And to be totally correct, you need to write the word float down here. That is the same thing as scoping. Each iteration has an independent variable. This changes the parallel task graph. The parallel task graph can work with a sum variable for every iteration of this outer loop. Okay? For every iteration of this outer loop, a unique sum variable will give us flexibility in the parallel task graph. It takes the task graph from a chain to several one independent task, at least, for this outer loop. Okay. Another way you could have done this is just eliminated sum entirely. If you eliminate sum, if you strike through this, you strike through this, you strike through this, you line these two up so that y of I plus equals these things, and you also would have gotten full credit for that. That's more the thread local storage approach, although the idea is the same. You're breaking up this dependency on sum for every iteration. What software component determines when a thread is allowed to run on your computer? To be clear, this question is asking you, on your computer, what tells an existing thread to run at a certain time? What software component matches a thread to a hardware core at a specific time? We spent a lot of time talking about this topic. The correct answer is scheduling, or more precisely, the OS scheduler. The OS scheduler decides on your computer when your threads run, at least in the ways that we've talked about threads so far. You got full credit if you wrote OS scheduler, kernel, these sorts of things. Generally, the compiler does not schedule threads on modern computers, but it does do a little bit of scheduling, kind of at the instruction level. And you can design a system where the compiler does a lot of your scheduling. But that's not really the answer to the question. So if you wrote that, you probably got half. Things like RAM, CPU, core, processor. To be clear, threads are scheduled on these things, but they don't decide anything. These components do not decide when your threads run, when which thread runs. And also, at the same time, these are not software. These are hardware. These are physical. You can hold this in your hand. So they don't really meet either of the criteria of the question. So that did not receive any credit. Okay, what's next? After the parallel region, that is after creating threads. So if we draw the picture, okay, we do pthread create. We create a bunch of threads that do what they want to do, whatever they want to do. Later, when these threads are done, when these threads have finished, but not necessarily after the threads have finished. The main thread is going to keep running. For the main thread to ensure all the parallel computation is complete, this is the key part of this, to ensure the parallel computation is complete before the next section of code, we need to, basically the question is, how do you turn these back into a single thread again? How do you go from one thread to one thread? After a parallel region, you join them. Hopefully you've written this code several times. You create the threads, you join the threads. Things like lock, unlock, destroy don't really have any meaning about. These things do not synchronize threads. These things do not join threads. I mean, mutexes, I guess, locks can synchronize threads, but locking does not ensure the parallel region is complete. Locking is used inside a parallel region, inside parallel code, inside threads to ensure safe access to specific data. But it doesn't have anything to do with thread completion. And likewise, exiting the program also. You need to join your threads before the program exits. Otherwise, well, there are side effects to that we don't really dig into. It more depends on the implementation and your operating system, but often it just means your result is incorrect. And possibly those threads never die, depending on what happens. Is the below function thread safe? Why or why not? Let's see. We have a global mutex. So every thread can see this mutex. That's what makes it global. You do share parts of your memory. If you recall from our memory diagram, each thread gets a stack. Global variables do not live on the stack. Global variables live way down here below the heap. The point being, they're not on the stack. They don't exist when main exists, then go away. So if they live down here, doesn't really matter where you think they live. They could live in the heap for that matter. Then we're using the same mutex, so that's fair. And then we lock the mutex when we modify A. Now A is the only memory, mutable memory that we access. I mean, B is mutable also. But changing B, right, we're not returning anything, so changing B doesn't do anything. It doesn't help us. So we're really only changing A. And then we unlock. And then we print A. And this is a race condition because you can change A. This is a write. And then you can read A. This is a read. And in the meantime, between unlock, again, this is a typo, but we addressed this during class, that this is unlock. The unlock is correct here. You can then, once you unlock, anything can happen. A can be changed by however many other threads exist. So you could say 3 plus equals 4 and have 7, unlock, go to sleep, wake up 10 years later, and then A is 572 because other threads came through and changed A in the meantime. I guess the diagram for that is maybe here you say A equals 5. You drop the lock. Another thread comes along and says, hey, A plus equals 7. So now A equals 12. This thread wakes back up when this one unlocks, does print, and it prints A equals 12. But it thought A was 7. We thought that, or whatever it was, A5. We thought A was 5. So yeah, this one has a race condition. Okay. Again, this is number 12 is the one that had a few issues. I'll talk about those real quick here. Again, generally, if you wrote, there were a few variations of this that got credit. So, and also I added 2 points just because of the extra difficulty that this one had. So draw the PTG and identify the work width and critical path. What would the length of the critical path be for size equals n? So you'll notice size equals 4 here. And so that's what I'm asking you is width, work, and path can be specific numbers because size equals 4. And I asked you to provide big O notation for the length of the critical path. So this is asking you to draw a PTG. And what I want to really get across about PTGs is that you don't really need to know anything about the code. You don't need to understand what it does. You don't need to understand how it works. You just need to be able to think at a very low level, what does a single line of code do? What data does it access is the key point. So when we read this code, we've got 2 loops. We've got a size variable that's clearly important. We use it up here, but we also use it down here. And we have an array variable, okay? So first let's look. Let's just start at the top. So size equals 4. Then for each iteration of I, so I from 0 to 3, we will do this loop. So I goes from 0, 1, 2, 3, okay? The first task, actually, let me draw this in a way that's more familiar because we have done a similar problem in class. You may just not have recognized it. So I equals 0. Well, what data do we access? We access array. I'm just going to write A for brevity. A0 on this line, or on this access, this is a write. We're going to write to A0. We're also going to read A0. And we're also going to access a, 0 times 2 is 0 plus 1. So we're going to access A at 1 as a read. Second task, A is 1. We're going to write to 1. We're going to read from 1. We're going to do I times 2. Oh, oops, sorry. We're going to read from 2 because A on this line is I times 2. So we access I times 2. 1 times 2 is 2. And then 1 times 2 plus 1, which is 3. Okay? And then we keep doing this. You get I equals 2, and you do I times 2. First is always we access the I value, so we access A of 2. That's our right. Then we access I times 2, it's 4. And then we access I times 2 plus 1, which is 5. And that's also a read. And then finally we do I equals 3, A at 3, right. 3 times 2 is 6, which you'll notice, by the way, that you're just counting up 0, 1, 2, 3, 4, 5, 6, 7. Okay, so once we've accessed all of these, once we've done all these nodes, we can look at the pattern. This is the first iteration of size. So what we notice here is we need to write to A1, and here we need to read from A1, so this is a read after write. On A1, or sorry, this is a write after read and then write. And then the same thing is true here, so we have write 2, read 2. So we do another read and then write. And that's on A2. And then we actually grow out of this problem. So we grow out of that. You'll see 3 doesn't show up at all in this problem. So these dependencies exist, but that's it for iteration size equals 4. Okay, so now we need to do size equals 2. That's our second iteration. That means we're going to have I values, 2 and 3. To keep ourselves organized, let's just write size equals 4 for this line. And up here, we'll do size equals 2. Okay. Now, we'll want to draw basically the same thing. We're going to do the same thing again. We know size equals 2, but our computation here doesn't actually change at all, right? We're going to count from 0 to 1 and access the data the exact same way. So you can actually copy these nodes. So you do I equals 0, A at 0 has a write, A 0 has a read, A1 also has a read. Same thing over here. We do I equals 1, A1, write, A2, read, A3, read. Okay, and then we find that this also has a dependency in this direction, right? Because we need to do the same thing. Likewise, we clearly need to do these tasks below here that have this dependency first. So this A, for example, A1 was the dependency here. A1 is also a dependency here. We need to write this before we read this. So you could draw a dependency here and a dependency here. The reason I draw this with a dotted line is this is a transitive dependency. You had to compute this, then this, then this. So you didn't actually need to, it wasn't okay to do this task immediately after this one. You had to do this one first. And so we don't show transitive dependencies generally because it gets too messy. And it's the direct dependencies really cover the difference. Likewise, for this one, we have a similar problem. We have this dependency on 2. So we have a dependency here. Now, the mistake I made in this problem, the reason it was hard is because I actually gave you the wrong version of this code. I have a different way to do this code that makes this problem simpler. You don't have this dependency. You don't have either of these dependencies, okay? Unfortunately, I didn't give you that one, but that's fine. That was the only addition, is these three dependencies. The second issue with this code is because this isn't the one I was going to give, this loop right here is incorrect. It should be less than or equal to 1, okay? So if you drew this much, you got full credit. So if we stop here, just real quick, the metrics we have for this, first we need width, work, and path. Well, width at any given time is really just 2, right? We just have our 2 here. Which, by the way, we actually have a dependency here also because we have our 3W. I stopped doing the problem early. But there's a dependency here. These are really both direct dependencies. You need both of these independently handled. Okay, so I won't draw that as transitive. I'll draw that as a direct dependency. So anyway, the width here is really 2. This is the only place we get any parallelism in this version of the problem for such a small size. For just size equals 4, this problem doesn't look great for parallelism. So if you're at size equals 4, that's fine. The width, if you wrote size equals 5. If you wrote width equals 2, that's fine. Okay. With work, 1, 2, 3, 4, 5, 6. We've only done tasks where each task is weighted 1. Path. Really, it's this whole area. I don't want to draw it because we're about to modify this to show you what the problem was intended to be. But this is the critical path. You've got to do these, and then this has a length of 4. Now, 2 things I want to address. One is the length, which I'll address after this problem, just so that, because I think the intuition will be better. If I had done size less than or equal to 1, you would have had one last node that depended transitively here and directly here. And this would have just been I equals 0. This is a binary tree. What this problem actually solves is a parallel sum. At every step, you are adding 2 elements together, 2 independent elements together, but then you're storing them in an array, the same array. So if I do some numbers here, let's say 5, 3, 4, 2, okay? What you're doing here is you're computing 5, 3, and 4, 2. So you get 8, you get 6. And then you are storing them in place. So what happens is we come through and we erase 5 and 3 and writing 8 and 6 here. And we're just ignoring the rest of this array for the time being. Then when you do the next iteration, you do 8, this iteration, you do 8 and 6, and you get 14, and that would go here. And that ends up with this return array equals 0. The final sum would go in array equals 0. So that is the intention. If you drew this, you also got full credit because even I made that mistake. So if you drew this and you update these numbers to match this, you should have gotten full credit. If you didn't, then let me know. The last thing though is that really regardless of which version of this problem, what you needed to notice is that this dependency, no matter how big size is, this dependency only exists for nodes 0, 1, and 2. So for a very large graph, let's just add a bunch of nodes. you would still only have the dependency here, and then it would go away. No matter how many nodes this is. If I equals 1024, size equals 1024, you'd have 1022 nodes, or 1021 nodes, with no dependency. Okay? So in general, if you generalize this problem, and you'd only do this for large problems, it's parallelism, you only use it really for larger problems, what happens is really the width becomes n. Width is the size of the number of elements in your array divided by 2, which is a constant, so it's n. Likewise, this critical path would be this, but no matter how big the tree is, it's still 1, 2 at each level. So you'd add 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. In practice, because that 3 is a constant, this 3 is a constant, then you end up with a solution for length that is 3 times log of n. Because the branch of any binary tree, the length of the branch of any binary tree, is going to be on the order of log base 2 over n. It's always true. It's the benefit of using a binary tree as a data structure. If you Google binary tree and you find the operations for binary tree, if you want to insert something into a binary tree, it's going to be on the order of log n. Log n is a much better number than n. This is why we often use binary trees instead of arrays. Even though in practice binary trees can be implemented with arrays. But that's another topic. So we'll move on from that. If you got some variation of this and you think you didn't get full credit, you're welcome to come talk to me. Although for most problems, if it was in that 2-point threshold, I'm not going to make any changes because you only, for any of these metrics, if they were wrong, they were worth 2 points. And the tree itself was worth about 5 points. So if you drew something that looks like this and you don't think you got full credit, then you can come talk to me. But again, most of it's intended to be handled with this 2 points. All right, number 13. So finish the for loop in main such that the vector addition is split into equal chunks and performed in parallel. I'm actually going to pull this code up real quick. So this is the code for the problem you were given. Oh, is this the right problem? Yes, it is. So finish this loop, finish the for loop in main so that you get the right thing. So again, you can assume you have whatever you need up here. If you had to write it, that's fine. Some people wrote some stuff like, okay, we have an int a, and it was malloc. That's fine. You didn't have to write this, but some people did to help them think about it. So you had something that looks like this, and of course you had an int in, or an int size, if that's what you want to call it, that is, whatever. So that's the way you can think about this. And then the correct solution here, this is the same problem as the coding assignment for assignment 3. The code is actually a little simpler, but the problem is basically the same. You've got 2 arrays, you're trying to split them up into a partition based on the length. So that means that you are looking at writing something approximately like this, where you're going to access v of I, right? We've got this vecprob structure here that happens to look exactly like the arguments to our vector addition function. So in practice, vecadd is just a wrapper function, which we've talked about a few times, that unpacks the arguments to look like what vecadd expects. This is just to make the code look much cleaner in vector addition. So for vecadd, you have a, b, and size that we have to fill out at each iteration to correctly pack this argument up. Before I fill this argument, let's look at why we're doing this. It's because the args argument here is what becomes args up here. We're passing in the arguments to vector addition. So no matter what, we are going to send in the address of v at I to vecadd to try to get the correct solution. Okay, so we need to set A, B, and size. Size B equal, equal, equal. It's actually easiest to just start with size. We have t threads, so we want each thread to do 1/10 of the problem. So size divided by t is the size. Some people asked, this is a little different if you had odd numbers, and I told you it doesn't matter. There's edge cases, and in real code you'd have to handle the edge cases. But for the exam, we're just looking that you understand the idea. So this is going to give us each t. This is this splits your array into a partition of size over t. To add some context to that, let's draw it out. So our goal here is to take two arrays and add them together. So you've got array A, you've got array B. They're the same size. They each have elements. Our goal is that, say we have two threads, we want to split this in half. Now we're going to use 3 because it's easier to see how this generalizes. So if we split it into thirds, what happens here is this array, let's just look at one array because it's the same for both. The goal is to do A plus B. Let's just look at one array because the solution is going to be the same for the other array. So we split this array into thirds. What's interesting, each third of this is going to be length size over 3. T is 3. Size over t. Size over 3 is how much the gap is between 0 and here. So we want to work with size over t. So here, the size is going to be, or the location is going to be A plus, so A is the beginning of the array. A is the address of the beginning of the array. A plus size over t. That's the first third. You start at A, you count to size over t. That's what vector addition does. You start at A, whatever address you pass in, we just call it A, but whatever address you pass in, and you go until size. So in this case, you go until size over t. The second thread, so thread ID 1, needs to start here. It needs to start at A plus size over t and count until A plus 2 size over t, right? It's the second third. Okay. If you wrote this more generally, I guess you'd write this as size over t and 2 size over t. So the plus A is just to get the right address. And then the last size here, often you'd call this n or size or whatever. This location is A plus 3 size over t, if you took it that far. And of course, t is 3, so this cancels out. In practice, what we need to tell vector addition, what we need to tell the function vecadd, is I want to start thread 0 at A, and I want to end at A plus size over t. I want to start at A plus size over t and go until A plus 2 size over t. I want to start at A plus 2 size over t, and I want to go until A plus 3 size over t. Those are our 3 threads. Those are our 3 starting points. The length at each step is size over t, right? And that's what vector addition expects. It expects a starting point. This can be a starting point. This is a legal starting point. And it expects an ending point, or not an ending point, it expects a distance. It wants to know how far you want to go. It wants to know how many times you iterate. So if you're starting here and you're going here, you want to go size over t steps, okay? So what that means then is for our code, we want to do a via I. The A element will be A plus size divided by t. Now the catch here is that the second thread needs to start at a different place. The second thread needs to start at 2 size over t, right? Well, the second thread is going to show up in this I. We use I to differentiate which section of the array we're working on. So we do I times size over t. You see? You can rewrite A, 0, this is 0, as A plus 0 size over t, which causes this to cancel, which is just A. Likewise, A plus size over t, 1 size over t, 2 size over t, and that's it. So I helps us differentiate what task we're actually doing, which is why we often use I to index our tasks in our parallel task graph. So A plus I times size over t. Likewise, we need to do the same thing for B. And that'll do it. So we set each argument to our function. And we set the size. The size is always the same. We want each one to do an equal amount of work. And then we hand our newly packed struct off to vector addition. And vector addition didn't have to change. Vector addition didn't have to do anything. We didn't have to modify the code for vector addition to make this parallel. We just had to tell vector addition to do a different task with the arguments to vector addition. So this is the right answer for this. I got a few different things. The most common thing is probably you do this. People wrote things like this. What does this do? Well, this creates 3 threads in threads that all compute the entire array. They all compute the entire array. So that means you're not doing, you're doing this in parallel, but you're doing the same work. You're doing the same task in parallel on many different threads. You're just making it harder. It's as if the analogy is, maybe you're building a house. And maybe you recruit 4 people to help you build a house. And if you do it this way, you're going to end up with 4 houses. And all of those houses are going to take the same amount of time as it took you in the original time. Sometimes that can be a good thing, but they didn't help you build a single house faster. You just duplicated the work. And in practice, this probably won't work because you'll have a race condition. So depending on what happens, you may end up with incorrect values. Probably not in this case, just because you're always doing the same thing. Actually, in this case, A will just keep getting bigger. And so you do have a race condition. You have a few different cases here. I think the one in your homework, you don't get A. It was slightly different because you don't do plus equals. You did C equals A plus B. And since you're not reusing C, then that will give you the correct answer. In this case, you will get the wrong answer. Your numbers will be way too high. And possibly some of the numbers will be even more incorrect. You'll drop values because of the race condition. Okay, so let's move back to our handout. Okay, we've got our last two problems here. So for 14, finish the thread-safe queue wrapper. Let's take a look at this code real quick. So in this code, we are asked to introduce, we're asked to make this data structure thread-safe, this wrapper data structure. Again, this is a wrapper data structure because it doesn't actually do any functionality. You don't have an implementation of our two common queue functions, push and pop here. We didn't implement push and pop. We called an existing push and an existing pop function in our queue. That's what makes this a wrapper. It just is code that encapsulates push and pop, okay? The purpose of doing that is to make it thread safe. It's to provide a thread safe version of this data structure without modifying the code. Likewise, we were asked to do coarse grain locking, which means coarse grain locking means we want to do the entire data structure. Coarse grain locking on a data structure, or on anything, primarily you hear this in data structures, means when you access the data structure, let's say your data structure is an array, only one person can access any piece of the data structure at the same time. So if I'm writing a value here, nobody else can touch this data structure while I'm doing it. So what that means is we only want one thread to be able to push or pop at the same time. If one thread is pushing, nobody else can push, nobody else can pop. That's what makes it coarse grain, okay? On your other assignment, you had fine grain, which usually means you allow access to parts of the data structure. If it was an array, I guess you could do fine grain locking. You could give each element its own lock so that you only lock one. When I'm writing here, no one else can write here. No one else can read here. But they could write over here because I'm locking this once. To do that, to do fine grain locking, that means we'd have to have a lock. We'd have to have locks for every single element of this data structure, which basically means we'd need a second array, the same size as the first array, to store all our locks. And this is kind of what you did in your hash table. You have buckets, and so you locked the buckets. Your buckets are just elements in an array, so you created an array of locks for each bucket. Okay, in practice, coarse grain locking is of course easier. It's not as performant. It doesn't give you high performance in general. But that's what makes it somewhat straightforward to implement. So I'm going to use shorthand here because, again, this is your exam. You can write the full code out if you wanted to. That's fine. I graded either. I've said before that syntax isn't really worth a lot of points unless the question is about syntax, which, of course, you're not having at this point. This is about, it's an applied question, but if you forgot to write pthread lock, I didn't take off any points. So in that same vein, you would want to create a mutex here. Of course, if you wrote pthread mutex t, that's right. So we want our mutex to be attached to our queue. I'll come back and talk about that in a second. So I'll make a comment that tells me to come back here in a second. Once we have this, our mutex is packaged nicely with our queue. Okay? So what that means is we can access our mutex by going queue mute. So the goal here is to call pthread lock queue mute, or just lock. We'll just write lock. You write lock mute, and then that will give you what you're looking for. Likewise, you unlock the mutex when you're done with it. Likewise, we do that down here. Now there's a slightly larger modification here because this does not work. You can't return and then unlock. Some languages have features that kind of make that work, but in C you really can't do this. So we do, if our Q is integers, it looks like it is up here with this value. So we need a return value. Now we can return the element. And this isn't problematic. There's no race condition here. Because you've popped it, it's off the queue. No one else is going to get the same value as this. So it's okay to return it after we've unlocked. So in practice, this is what we end up with. This is the correct solution. Some variant of this. Now some people did lose points when they gave me a solution that looks like this. Okay. I assume maybe this came from earlier in the exam is why you did it like this. This is making a global mutex. Instead of protecting one data structure, you're saying if this is my queue and I want to push onto it, I'm going to lock this. But also, I'm going to lock every other queue in existence because we all share a lock. So if you have 500 queues, you can only access one queue at a time. No other thread can access a totally different queue, which doesn't help us too much. It has potential to slow us way down because, I mean, the queue, if you have two separate queues, why would you not be able to access them at the same time? So in practice, this doesn't quite cut it. And so you lost a few points for that, but at least you got the idea of coarse grain locking. And so I gave you, sort of, and so we gave you partial credit for that. You really shouldn't pass in the mutex. You don't need to pass in the mutex in either of these cases, because in this case it's packaged in Q, and in this case it's the global. Adding a mutex here isn't quite right either, because it doesn't guarantee that it's coarse grain locking. It leaves it up to the user, the end developer, to use this. This isn't an effective library. They could use your code incorrectly if you add it as an argument. So you add the mutex to the data structure, you package it with the data structure to ensure that each queue has its own lock and each one can be coarse grain locked separately. Making it global is way too coarse, way coarser than anyone would expect. It's like if you locked your car, but also when you locked your car, everybody else's car also had to be locked. Okay, so now let's move back to our last question. So this is our last question. Draw the ideal Gantt chart assuming we have 3 cores and use stack scheduling for the following code. So if you were there for our last class, you know that pragma OMP parallel 4 means that you are going to kind of automagically parallelize this code. So if we draw the task graph for this code, what we find, and that's the right thing to do, by the way. If you don't know how to do it directly, we can use a parallel task graph. The key, the magic of a parallel task graph, is that you don't need to know anything about your code to draw the parallel task graph. You just have to read the code and find each task. And you can use a parallel task graph to solve all kinds of problems. Parallel task graph is meant to be a tool you can use to solve problems if you don't know how to solve them any other way. It's something you can always fall back on to help you understand parallel problems. That's why we use them. And they don't require anything. There's no trick to them. You can just follow the steps and it will always give you the right task graph. So in this case, we don't have any dependencies. CI, AI, and BI are always separate. So we have none. Okay, well, that's straightforward. Now we said we want to draw a Gantt chart. Well, a Gantt chart always looks like this. You got time, Okay, and then the y-axis, x is time, y-axis is our CPUs. So in this case, we have 3 cores, so you can do CPU 0, 1, and 2. Okay. Now, in a Gantt chart, we draw the schedule of the parallel task graph. We draw the schedule that we want. We were asked to provide a static schedule. Static schedule is decided at the beginning of time. We're going to partition our tasks. I think this might have been not quite, this was either the problem we did in class or it was very similar to it. If we assume each one of these takes a time of 1, then we can just start picking tasks to schedule. To be static, you want to put the closest tasks together. So if it looks like this, and we do I++, then when we do a static schedule, you want to cut it into 3 pieces because you have 3 cores. So you take all the numbers, or actually we could do it up here in the task graph. You take all the numbers. We know we've got 3 cores, so you draw 3 lines. 1, 2, or you draw 2 lines, right? And you've got 3 partitions. Then we draw them together. 1 core gets I equals 0 and I equals 1. Another core gets I equals 2, I equals 3. Another core gets, and these are supposed to be the same size. I didn't draw them the same size, but everything ends at 1 and 2. I equals 4, I equals 5. When you draw these, you want to be a little more deliberate than I am trying to draw sideways. You'd like them to line up pretty close to directly. And that's it. That's the whole thing. You know that you've got exactly 6 tasks. You know they're going to go on 3 cores. That means each task is only going to get 2, or each core is only going to get 2 elements. Each element has a time of 1 because you weren't given anything else. And there's no heterogeneity. All of these tasks are homogeneous. They're all the same task with a different I. So yeah, that's the whole thing. You schedule them with the one side by side. The reason you schedule them with the one side by side is first, it would be harder to write a scheduler that splits them up. Second, this is more how caches work. This is what your computer wants you to do, is have sequential data accessed sequentially. Computers do not like random data access. They like sequential data access. And that's it. So if you drew this, you got full credit. Some people drew a variety of things. I'm guessing some people tried to fall back on something they might have seen in 2181 or 3181. That didn't quite work. We, at this class at least, do not really split up operations like this. There's really no way for us to do this. This might be happening. You might be splitting operations up, but there's no task C. There's nothing to do with just C. I mean, you can write the data to C, but it's not really what we're doing here. We're trying to schedule our tasks, figure out when the tasks would be completed at a given point in time. So in any case, overall, I think that's the end of the exam. Grades on this were actually not terrible. Of course, you always have access to statistics on Canvas. Those statistics are skewed by a few outliers in the course. In general, the average on this exam before I applied a curve was around a 73, so the curve applies a 75 average, which is about what you would expect if it was a bell curve. The highest grade was not perfect, but it was over 100, and there actually were several grades over 100, even without the curve. So some people did very well in this exam, some people didn't do so well. I recommend that you come back and watch this video in 3 weeks before the exam. I recommend that you study this material, go back and read about these things. If you don't really understand parallel task graphs, you really want to understand them, we're going to use them. At least on your exam. We may talk about them while we talk about MPI. You still need to know Amdahl's law. You still need to know how to do C programming. You still need to know how memory works. You really want to understand how, local variables and structures work. This is really just object-oriented programming. You've done this a lot. Your structs are objects. It just requires a lot more deliberate typing. You have to do the steps that usually the compiler does for you, or that the language runtime does for you. But otherwise, all of the material on this exam, all of the problems are problems we've more or less done before. So, in some form or another. Even this one, even number 12, okay, a very similar task is the prefix sum. You may remember the prefix sum problem that we covered in class. It looks like this. You do the sum, you do the sum, you do the sum, you do the sum, and then you distribute the results, and you end up with a binary tree and then an inverted binary tree to do the prefix sum. Well, the first half of the prefix sum, and we talked about this in class the 2 days that we did this problem. Prefix sum, the first half, the bottom half, is just a regular sum, which is similar to the way this one does it. It's just when we did this in class, we didn't do it in place. We did it out of place. But otherwise, the tree is almost identical. So we've mostly seen these problems before. So if you have trouble with these, I recommend the normal strategies. You go back, you practice your homework. If you have questions about your homework, if you don't understand your homework, if you didn't make the grade you wanted to on your homework, you should come talk to me. Email me, set up a meeting. I have office hours. What I mean by office hours is that every Monday, Wednesday, I am in my office, and my entire job during that time block from 1:30 to 3 is to answer your questions. I don't have anything else going on. I don't have any conflicts. Unless I tell you in advance I have conflicts, which I think has only happened once this semester. I am here to answer your questions. So if you're behind, now's the time to catch up. Otherwise, thanks for hanging it out through this entire video. If you watch this, well, hopefully that will help you on your final exam. These concepts will come back. In any case, we'll see you in the next video.